All right, and we are live. Welcome everyone to our Facebook Live today with the SETI Institute, and we have here our FDL team. The Frontier Development Lab is an applied artificial intelligence research accelerator. We bring together the brightest minds from around the world in space science and exploration domains, paired with machine learning researchers to tackle problems in the areas of heliophysics, astronaut health, lunar exploration, and earth science. This is our 5th year of the FDL program, hosted by the SETI Institute and in partnership with NASA, and the very first year that we have taken the FDL program virtually. We have 8 teams this year at FDL US going through our 8-week program, and we're currently on week 3, where our teams are narrowing down their focus and preparing for their milestone review. Today, I have with me our Starspots team, and I'm going to go ahead and kick things off with some introductions. So I'd like to ask our researchers if you can go ahead and say your name, your affiliation, where you're located, and the work that you're currently doing. So I'll go ahead and turn it over to Tansu first.
Hi, Zara. Thanks, everyone, for the invitation. So I'm Tansu Daylan. I'm a postdoctoral research fellow at MIT. I'm based in Boston currently. I work in general on exoplanets, exoplanet transits as part of the TESS team, which is a NASA experiment to look for exoplanets. And in this team, basically, we're working on this nice challenge, which we'll be presenting very shortly.
Great. Thank you, Tansu. And we also have Lisseth.
Yes, hi everybody. My name is Lisseth Gavilan. I am a postdoctoral researcher at NASA Ames Research Center. I work on experimental and laboratory astrophysics, basically focused on the evolution of cosmic dust, interstellar dust. And we perform experiments in the laboratory to understand how these dust grains evolve, and there are different types of radiation and physical processes.
Wonderful, thank you. And we'll go to Emmanuel.
Hello, my name is Emmanuel Johnson. I'm currently located in Valencia, Spain. I'm doing my PhD at the University of Valencia. I've been here for about 3 years now. My current work is I deal with a lot of probabilistic machine learning methods. We try to apply them to interesting problems that stem from climate science to remote sensing, and also oceanography, so things of that nature. So yeah.
Great, thank you. And I'll turn it over now to Stela.
Hi everyone, I'm Stela. I'm currently in Maryland. I'm doing my PhD in Catholic University, and I'm a research assistant at NASA Goddard. So I'm an astrophysicist, and I work with planet detections, and I'm currently applying machine learning techniques to improve this methodology.
Great, thank you, Stela. And we have Daniel.
Hi, I'm Dan Giles. I am a PhD candidate at the Illinois Institute of Technology. I'm currently living in the Bay Area. My PhD research has been working to find the most interesting, the weirdest stuff in sky surveys. So I started with the Kepler data and applying unsupervised machine learning to just try and identify those weirdest things, either astrophysical in nature or based on data artifacts, whatever it may be.
Great, thank you, Daniel. And thank you to all of our researchers that are joining us today. I also want to take a moment to thank our viewers that are joining us from, it looks like Pakistan, Surrey, UK, Santa Cruz, California, Madrid, Spain, and Bremen, Germany. So thank you guys for joining and welcome. So to kick us off, I'm going to go ahead and ask a few questions, and then we'll take some audience Q&A. So first off, I'd like to dive into the challenge. So Tansu, can you go ahead and explain what the challenge is that you are working on?
Sure. So basically, we are interested in a phenomenon called starspots. Essentially, we know the solar analog of this, the so-called sunspots, which are relatively cool regions on our star, the sun. And we kind of naturally think that the same phenomena must apply to other stars as well in our galaxy. And the idea is to basically study these so-called star spots through basically data collected as time series. So you measure the brightness of other stars as a function of time, and then you try to infer the distribution, the multiplicity, how many of them there are, what's the contrast, how opaque they are, these sunspots on other stars, and what these can essentially tell us about potential habitability of exoplanets, so-called planets around those stars. And what we can know about them using this type of data. We basically use data collected by spaceborne experiments like TESS and Kepler from NASA. And we are using machine learning methods basically to learn about these. That's our challenge.
Great. That's a wonderful overview of the challenge. And I would really like to turn it over now to Lisseth, if you can share with us, why is this challenge important?
So it's important to learn about these star spots because they are manifestations of the magnetic activity from the stars, like our sun. So by understanding how this magnetic activity manifests in other stars, we can really learn more about our own star, the sun, and the potential effects of this activity on the Earth and the Earth weather, for example. We can also, by learning more about the physical properties of these stars, we can learn how they influence the planets around them, the exoplanets. So we can really constrain the potential of these planets to eventually host life. So this will be directly impacted by the properties of the host star in these systems.
Great, thank you, Lisseth. And I know that you guys are really early on in the process for FDL. So we're on week 3 out of 8. So you have a ways to go. But I was hoping, Emmanuel, if you could kind of give us a little bit of an overview of some of the tools and processes that you're using to address the challenge at this early stage.
Right. So as you said, we are still in the early stages. But the most important thing I have to highlight that is special about our group in particular is the emphasis on communication. So we have a lot of tools, and we've really focused to make sure that everyone is heard and everybody is able to express their opinion, and that anytime there's a change, everyone knows about it. So we use things like Miro and Trello, which allows us to put sticky notes virtually, which is a fantastic tool. On a more technical approach, most of the team, we've all kind of decided organically that we want to take a more we want to take a safe bet where we look at simulated data from already known models and try to use neural networks, which is, the hot topic, I guess, greatest machine learning algorithm out there right now. And we're going to fuse this approach of looking at simulated data, which we know that we'll be able to learn, and then we'll be able to fuse this, or at least kind of transfer our knowledge over to the real data approach. And then on the even more technical side, if you really want to geek out, we do like to use, cloud computing resources and things like that. So Google Cloud Computing Services has been fantastic to allow us to really take advantage of the computing power to be able to actually, get things done within a matter of 9 weeks. And then, other things like sharing code and things like that from GitLab. And of course, our Slack channel, which is mainly for emotional support, but also just communication as well. But yeah, definitely emotional support as well, to know that even though we're so far away, we're still able to communicate with one another. So I'd say those are the big ones.
Great, thank you, Emmanuel. And I do think that you're right with FDL. You guys have access to vast amounts of compute resources, which is a really cool aspect of this program and makes FDL what it is. So thank you. So I'm going to go ahead and turn it over to Daniel. If you can talk about any sort of pitfalls or roadblocks that your team is experiencing, or just hurdles that that your team has to overcome in the coming weeks.
Certainly. So I think like the first part of it, Tansu mentioned, the data that we're getting in is time series data. It's just brightness over time. So the data isn't like super complicated. It's actually very simple, and we're trying to extract kind of really complicated information out of that. Specifically, like we're trying not to just identify whether or not there are spots. We're trying to identify if there are multiple spots, what those spots look like. And to get that out of a light curve is a pretty complicated endeavor. So that's one of the challenges that we're facing, is trying to figure out exactly how we're supposed to do that, or how accurate those maps can even be. And that's kind of why we're using a lot of simulated data, is because for that simulated data, we know what the ground truth is, what that actual answer is, what the spots look like in the simulated data. And that's that ties into part of another roadblock that we have, is that we don't know what the truth is for a lot of the real data. So we do know it for the simulated data, which is why we want to use it. But the ground truth that we have from real data is very limited. We have a few stars that we know what it looks like. We know what the sun looks like, obviously. And that's probably our greatest source of like physical information about what these star spots are going to look like. But we have a very limited amount of the actual data that exists. I think another maybe less technical challenge is that we're all kind of from different realms, but that's both a benefit and a challenge, is that we talk about things in kind of different languages. So we have the ML background, we have the astronomy background, and we talk about things and do things in different ways. And we're trying to figure out that how to make those mesh in the best possible way. We were just talking about how astronomers like to store all of the data for a single source in one location in a single file. And like from a machine learning perspective, that's a very weird way to do things, because you have a single time series in one file, and then you have 2 million light curves. So then you have 2 million files, and that's maybe not like the best from a data perspective, but for a physical perspective, like we want to keep all of the data in one place, and we don't want it to mingle too much with other stuff. So that's kind of one of the less technical things, I think.
Great, thanks, Daniel. And I'm really excited to see how you guys progress and work out these challenges in the upcoming weeks. And I think one of the biggest challenges for all of us at FDL is, again, this is the first time we're taking it virtual, so we're all exploring that as well. So thank you, Daniel. And I would really like to now turn it over to Stela to talk about the desired outcome. What do you hope to achieve at the end of FDL?
Yeah, so as everybody mentioned, we are studying starspots, and starspot give us a lot of information that it's essential for stellar measurements and to understand how stars are, how they evolve, how they affect us. And well, the holy grail of all of this, it's something called differential rotation. That is basically how a star rotates in different parts of it, because we have a star that it doesn't rotate uniformly. So you have like the middle rotating at a different speed than the top. And the star spot will be essential to figure out this, because it gives a lot of information about how the star is evolving in time. So I hope I think all of us, we hope to get more information about spot lifetime. We want to know how quick the stars rotate. We want to know if we can get an idea of the coverage area that the star spot is occupying on the star. So basically get all these properties that star spot tell us and be able to get the parameters so we can apply for other things.
Great, thank you, Stela. And thank you to the rest of the Starspots team. That was a great overview of where you guys are currently at and where you guys are heading. I also want to say welcome to our viewers that are joining us. So we have folks from Hungary, Norway, France, Bosnia, Brazil, Malaysia, Arizona. There's so many different people that are viewing, and we just would like to say thank you. So we're going to open it up to Q&A, but before we do that, I just want to turn back to the rest of the team to see, what do you guys hope to get out of FDL? It doesn't necessarily even have to be like, what do you hope to better like learn from the challenge, but what do you hope personally to get out of FDL? And to kick us off, Daniel, are you okay with going first?
Sure.
Okay.
So Personally, I'm really excited to be learning about all of the different methodologies. This is a bit of a different realm of physics than I normally do. So I'm excited to learn about this different realm of physics and how important it is to understand like differential rotation of stellar bodies and how they inform us about magnetic activity and how they tell us about the evolution of stars. But I'm also really excited about all of the different machine learning that I get to kind of experience, because I've mentioned I do like unsupervised machine learning, but that's just like one very small application of machine learning. And I'm excited to get into kind of like neural nets and figure out exactly how they work a little bit, because I don't know that much about it. And I'm just excited to work with these different professionals and experts to increase my own skill set, I guess.
Great, thanks, Daniel. And how about Lisseth?
Same as Daniel, I'm really excited about learning more about these different machine learning techniques and to discuss about their applicability in different astrophysical problems and problems that are really state of the art. And just I'm also really excited about working as part of this diverse team, problem solving together, and how we can reach a consensus on the most optimal ways of addressing this problem in this short time window that we have. So it's really interesting, this set of new hard skills in machine learning, but also these soft skills of team building and team problem solving.
Awesome, thanks, Lisseth. And we'll move over to Tansu.
Sure. So I guess I'm very excited because this is also outside of my expertise. I normally work on exoplanet transit data to characterize and find exoplanets. And this is certainly orthogonal. I'm learning whole new problems, starspots, and how they can be relevant to our exoplanet science. And I'm also coming up with new methods of looking at this new problem. So it's definitely a great exercise, intellectual exercise, to think outside of the box and do some research that's outside of your comfort zone, basically.
Great, thank you. And Emmanuel?
Yeah, so to pivot off of what the teammates said, you want to talk about outside of the box. I don't do anything to do with space at all. I'm pure machine learning on everything on Earth. So this for me is completely outside of my comfort zone. So as a personal goal, I would really like to be, I guess it's been really comforting to know that I have learned a lot just in the past 3 weeks, just because of the support I've had from the team, as well as the willingness for them to explain, and we go back and forth. And I learned quite a lot. So by the end of the 9 weeks, I'll be able to describe the title and tell anyone exactly what we did. And I'm looking forward to that. And I guess on a softer skill note, based on what Lisa said, the organization has been phenomenal with this team. And it's something that even together, it's a difficult thing to do when you have 10 people and they each have an opinion. How do you get each opinion? How do you enable everyone to have a voice, so they don't feel left out or they feel bold or things like that. And this is virtual, and still I feel quite satisfied that my voice has been heard. I've heard everyone else's voice, and we're all managing to communicate and work together. And if we can do this virtual, based on a virtual board with sticky notes, imagine the kind of thing we can do in the future together in person. So I'm really looking forward to see how personally I grow, I guess, as we all grow as researchers in the future. So that's kind of on a softer note, something I'm looking forward to.
That's great. Thank you. Very well said. So I'm going to go ahead and read some questions from the audience. So we have Marco, who has a question on how is classified the differential rotation of our sun. Trying to think of how that would be.
I mean, I think this question kind of gets just at does our sun have this differential rotation? And the answer is yes. So the center of the sun is rotating faster than the poles. I don't think I have that inverted. I think that's right. And what that causes to have happen is the kind of the insides of the sun are twisting and turning a little bit, and that's why we see this the phenomena of star spots appear, and they actually appear at specific latitudes based on the differential rotation. And that kind of influences the stellar activity cycle, and so the sun is rotating, and the sun is rotating at different speeds. I think that's how I would answer that question.
Great. Thanks for that answer, Daniel. And while we're checking out more questions, Stela, I wanted to turn it over to you on a more personal level. What do you hope to get out of FDL?
So as everybody mentioned, FDL is an amazing experience because we have people from all over the world, different backgrounds, and we kind of we are working together, and it's a very different dynamics than what I'm used to, because as a scientist, I'm used to be working with my own data, and now we are collaborating all the time. We have a very nice way to organize things, and even though we are splitting in small teams, we are working together all the time, and I was really impressed that we are doing this virtually, and we are intensively collaborating together and learning together how the other do the same thing as you want to do, but taking different paths. So it's amazing to see how everybody thinks of the same problem, how they aim to solve the problem. And I don't know how they do this in FDL, but as Emmanuel said, everybody's heard. So I feel like we were able to really get all the ideas and converge. So yeah, FDL is amazing. And we also have all the resources. We have Google Cloud. We have yeah, I don't know. It's great.
Awesome. Thank you, Stela. And I think we're still looking for any additional questions. I know that you guys did a sprint for your first week. Does anybody want to describe how that was and what you guys got out of that?
I've already spoken, so somebody else should say something.
Okay. So regarding the sprint week, I'd say for me, it was to understand the title of the question. And as a team, it was to make sure we all understood and that we all were able to put our opinions down on paper. So remember we talked about how somehow we were able to get everyone's voice heard. It was really an intense, 4 to 5 hour session of just sitting down and saying, okay, this is what we have given to us. How would you solve it? Right? And then the next person, how would you solve it? And then listening to the other person to find how would they solve it. And then picking the best parts of each solution. And then somehow it was magical, just starting with, you could say noise, and everyone has their own opinion. And somehow we managed to, as Stela said, converge to one solution. So that sprint, I would say, was really key in us actually, getting to week 2 and 3 and such like that, where it was mainly to make sure that we were all speaking the same language, that we were all understanding the problem, and that we all kind of had heard everyone else's opinion and had somehow made those opinions our own. So it was really a sprint as a team, and to make sure that the problem kind of was set for all of us. And then from there, we went on from there. So, yeah.
Great. Thank you for giving some insights into the process that you guys used at the very beginning of the FDL program. So I think that we are at time. I just wanted to say thank you to all of our researchers, the Starspots team that joined us today. Really appreciate you taking the time. And thank you to all of our viewers that were able to join in from various locations around the world. And thank you for joining this Facebook Live.